This board is RFL-RFT RF trainer kit. In this board we are complying various types of transmission channel as well as the transmission line discontinuity. There are the two parts are there. This part is actually related with discontinuity and these portions is related with your transmission channel. There is in our earlier video we covered open air transmission channel, coaxial transmission and microstrip. Now we are going to demonstrate the CPW, coplanar waveguide. Coplanar waveguide is the a transmission channel which is looking like closer to the microstrip, but there is one difference is that here you can see the CPW with ground. With ground means this is the microstrip line, but the ground is placed at this side and this side. So at the both side the ground is very near. The ground is very near, so in between that small gaps are they are going to be maintained, and this gap and the width, by using this we can calculate the impedance of the CPW. The CPW impedance of the 50 ohms or whatever 60 ohms or 800 ohms, that is depend on your strip width as well as the gap. These two parameters makes the impedance ratio. And also this is the ground which is very nearest. Why CPW is popular in the RF? Because of the many times you have to make sure that your component coupling capacitors or your transistors have the look for the nearest ground. The nearest ground, if you provide to like this is the active line and this is the ground line, so you can connect between these two lines easily your component, and the component gets nearest ground. So if they fails the nearest ground, the noise floor of the overall devices is going to be lower. This technology are mainly made for the multi-layer RF circuits. This side you can look. This is the actually PCB side where the middle is your strip line and the both side there is a ground plane. So this ground plane basically having the equal lengths we are separated. So this is the CPW with ground, and the next experiment we have the things that is CPW no ground. Means here and here the ground is provided, but at the back side there is no ground provided. So see this difference, this is the entirely metals are there, here is no metals are there, or here is also no metal, only this is the white ident is there. This is a picture but not ident. If you put any multimeter, you are not getting any continuity tone over this area because this is the with no ground. So CPW with ground and without ground we are going to be compared in this experiment. Frequency again we keep it at from the lower side to higher side 10 megahertz to 1.3 gigahertz. Okay, so almost straight lines we are getting here. 0.5 dB, 0.6 dB loss is there, and the higher frequency side is you can observe also the flatnesses are there, is mainly made for the high frequency, so you are getting very low insertion loss with the CPW with ground. Now we are connecting CPW with no ground. Loss was little bit increases. Earlier that is a 0.2, 0.3. Now it is 0.5, 0.6 is there. Little bit is loss is going to be increased in the CPW with no ground. When at the lower side the ground is not there, somewhat little bit loss is going to be increased because of the propagation within the dielectric that affects here, and here the perfect boundary condition they meets, that's why the loss is going to be optimized. Here the loss is not optimized because only the upper side ground plane is there, microstrip is there, active part is there, lower side nothing is there. When the field comes at the lower side of the dielectric or the FR port, he can't find out any metallic surface over there. The metallic surface is not at there, so somewhat the losses is going to be increased. So here the all CPW lines are propagating in the dominant mode. So in the dominant mode we can compare that little bit noise loss is going to be added over here. So thank you.